Okay, in this first part of the video, I am finishing example 2 from class, but I'm going to go ahead and just go from the beginning again. So the first question was, what is the degree of this polynomial? And the polynomial is the square of x minus 5 times x minus 7 times the cube of x plus 4 with that negative thrown in front. If you want to know what the degree is, you need to think about what would happen if you were to multiply everything out. So if I were to multiply out x minus 5 squared, I would get an x squared plus some stuff. And then I'd multiply by x minus 7, and if I were to multiply out this cube, my highest degree from that would be x cubed, and then plus some stuff. And then if I look at multiplying all of those together, I am going to get a negative x squared multiplied by x cubed, which ends up being negative x to the 6th. So that means that this is degree 6. The leading coefficient is negative 1. Now the zeros are given just by using the zero product property and looking at what would zero out each factor. So each of our zeros, we have 5, 7, and negative 4. The multiplicity is just the exponent that appears on that factor. So on x minus 5, which is where the 5 came from, that's multiplicity 2. On 7, it's multiplicity 1. And on negative 4, it's multiplicity 3. If all of your zeros are real, so you can fully factor out and not have any leftover polynomials, then the multiplicity summed up is actually the degree. So if you just add those all up, you get 6. Now the behavior at the root is just whether the polynomial bounces or crosses. So when you have multiplicity 2, you want to look at just that part. That looks like a quadratic piece, and so it's going to behave like a parabola. So it is going to bounce like a parabola. Similarly, the x minus 7, just that part looks like a linear function, so it's going to cross like a line. And then the last part, the x plus 4 cubed, it's going to cross like a x cubed does. So an x cubed crosses the x-axis like that or that. The last question is the y-intercept, and to find a y-intercept, we let x equal 0. So I do f of 0, which is the opposite of, then I have negative 5 squared times negative 7 times 4 cubed. And if you multiply all of that together in your calculator, you get 11,200, which is a huge y-intercept. So let's go ahead and take a look at what this graph might look like. So I've got my x-axis, and I'm going to go ahead and put my zeros on, negative 4, 5, and 7. And then my y-intercept, I don't have to use the same scale for the y's, so I'm just going to place it at 11,200. We know it's a degree 6 with a negative leading coefficient, which means in the long run, both of the arrows have to be pointed down. So then I just try to connect all of the information I have. I need to come from this arrow up toward this 0, and at negative 4, I'm going to cross like a cubic. So I'm going to come up, and I'm going to cross like a cubic does. Then I need to somehow make it to that y-intercept. Maybe there's a high or low between, I don't know. So this part, I'll highlight the part that we're not really sure about. We're not really sure what happens in here. We're not really sure what happens in there either. Okay, now I need to head down to that other x-intercept at 5 where I'm going to bounce. So I head down, and I need to bounce like a parabola does. So I do something like that. And I know I need to turn back around because I need to cross through this other x-intercept like a line. So I'm going to turn around somewhere and cross like a line and just meet up with that other piece. So these parts where I have my turns and things outside of the x-intercepts, I don't really know what that looks like. But what I do know is sort of what happens near each root. So this behavior we're pretty sure of, and we're sure of that point. And we're sure of this end behavior. So those green parts we're sure of, but the other parts not so much. if we want to check our work, we go ahead and verify in Desmos. So I've put the Desmos graph in and notice that I was wrong on at least one major thing. I was wrong on which side this turn was of the x-axis. And we don't really have a way of knowing that without doing some more calculations using calculus, which is not what we're ready to do. But we do seem to have the right behavior around 4, we have the right behavior around 5, we have the right behavior at 7, and we have the correct value for the y-intercept. The only difference is where I put that turn. So that is basically what we're doing. Remember, only focus on the things that we can answer, which are what the function does at each of its zeros, what it does in the long run, and what its y-intercept is. So those things that I've circled in green here on the video. Hi, this is Mrs. Villette, and this is a short video to remind you of factoring by grouping. So factoring by grouping is a technique that we use when we have 4-term polynomials. And it's a way that we can obtain the factored form, which we know is useful for, and we were supposed to fill in the blank here, the factored form is useful for finding the x-intercepts, or roots, or zeros of a function. So we're going to consider this first example. It's a 4-term polynomial. It's cubic, so the highest degree is 3 and the leading coefficient is 2. And for this polynomial, there's actually a typo that we need to fix. We need to change this negative 5x to a negative 50x. So here's how factoring by grouping works. It's very similar to what we've done in the AC method. I am going to put a plus sign here in the middle of my polynomial to split it into 2 groups. Now from each of these 2 groups, I factor out whatever the GCF of that group is. So the GCF on the first group is x squared, and the GCF on the second group is negative 25. So I have x squared times 2x plus 3, subtract 25 times 2x plus 3. Now I notice that between these 2 groups, I have a common binomial factor of 2x plus 3. And I'm left with x squared subtract 25. Now hopefully you notice that x squared subtract 25 is a difference of squares, not cubes, so it's a difference of squares. So we can go ahead and just do one more step, which is to expand out or factor out that difference of squares into x subtract 5, x plus 5. Now the next directions say to plot this function in Desmos and choose a viewing window that clearly allows you to see all of the intercepts. So hopefully you already recognize that this factored form is going to tell me intercepts. The intercepts are clearly 5 and negative 5. And on this one we have to do a little bit more work and set 2x plus 3 equal to 0. 2x is negative 3, x is negative 3 halves. But our actual answer to this first part was the factoring by grouping. The other thing you hopefully notice is that the constant term is negative 75, so that's my y-intercept. So here's a graph from Desmos, and notice that I've had to adjust the y-scale considerably in order to see that y-intercept of negative 75. I can see my x-intercepts at negative 5 and positive 5 from the difference of squares, and at negative 1.5 or negative 3 halves. Part C asks us to figure out how do those zeros relate to the factored form. Part C asks us how do the zeros relate to the factored form. So notice that our zeros were negative 5, negative 3 halves, and positive 5. And our factored form was 2x plus 3 multiplied by x minus 5 multiplied by x plus 5. Now each of these zeros, when I plug it into the x of a corresponding factor, will zero out. So if I plug negative 5 into the factor x plus 5, I get 0. If I plug negative 3 halves into this factor, 2 times negative 3 halves plus 3, I get 0. If I plug 5 into this factor, I get 0. So this is just the regular zero product property. And it's just applied to a higher degree polynomial. We were using it for quadratics before. So the last example in this video is another factoring by grouping. And we're going to do the same thing as we did in the last one, just separate our 2 groups, factor a greatest common factor out of each. Ooh, something unexpected happened here. I did not get a common factor between these. So what that must mean is that this is not factorable using our technique of factoring by grouping. Notice my two binomials were different, so it didn't quite work the way that we wanted it to. So there's a couple things we could do. One is we could graph the function and see if it had any real roots. So here's the function, and I've marked off where the zeros are, and they're not at nice numbers, so they're not at nice integer values or even rational values. The 0, -10 is okay, but the rest of them are kind of not nice. I'm guessing that I made another typo when I was going through. I had to retype some things on these notes, and I'm guessing I actually made a sign error. So let's go back and fix the problem to what I think it should have been in order to be factorable. Let's go back and change this to a +10. If that is a +10, then when I factor out this -10, this will now be an x subtract 1. So now I have an x minus 1 as a common binomial and an x squared subtract 10. Similar to the last problem, we want to check if the second factor is factorable. And x squared subtract 10 almost looks like a difference of squares, except 10 is not a perfect square. There is something that we can do here which is kind of handy. Although 10 isn't a perfect square, we could write it as the root of 10 squared. So we could write this as x minus 1 and then treat this like a difference of squares. So the square root of x squared is x, and the square root of 10, well, is just what it is, square root of 10. So I'm going to say root 10 on both of these, and then just make one of them a plus and one of them a minus. Just so you can see that that actually is a valid technique, go ahead and multiply back out. X times x is x squared. Then I get a plus root of 10x and a minus root of 10x, which zeroes out, and a minus root of 10 times root of 10. The root of 10 times the root of 10 is just the square root of 100, which is, of course, just 10. So I get x squared subtract 10. So, not at all what I intended with these two problems since there were typos in both, but once you fix them, hopefully you get the idea of factoring by grouping.